So now we come to the exciting part of the course where we start our study of special relativity. And as I said in the introduction, Einstein's special and general theories of relativity are some of mankind's greatest intellectual achievements. But principles of relativity have been around from before Einstein's time. And in particular, we have Galileo, who was born 1564, lived until he was about 80, 78. He rethought traditional ideas about force and motion. And these were ideas that were plausible and had been upheld by all authorities for many centuries, but were in fact misleading. Okay, so using his own experiments, he created a new science of mechanics. And in his 1632 book, called Dialogues Concerning Two Chief World Systems, which was quite a famous book that got him in a lot of trouble. It was later put in an index of forbidden books for a couple of hundred years. But in this book he said the following. So this is on Galilean relativity. He said, "Shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies, some butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the little animals fly with equal speed to all sides of the cabin. The fish swim indifferently in all directions. The drops fall into the vessel beneath, and in throwing something to your friend, you need throw it no more strongly in one direction than another, the distances being equal. Jumping with your feet together, you pass equal spaces in every direction." And this is the key point. When you have observed all these things carefully, so imagine yourself on this ship in the deck, have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way and that. Okay, so you're below deck, you can't see out. The ship is moving uniformly, which we interpret as constant velocity. And this is the key. You will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. Okay, and we've all had this type of experience where maybe we've sat in a car and a car beside us has started reversing, and then we jump because we think we're moving or sitting on a bus. So this is Galilean relativity. Okay, so we're going to look at ideas from Newton, and then we'll see what the problems are with those and where Einstein comes in to fix them with special relativity. And then we'll spend the next few videos discussing the consequences of special relativity and how it completely changes or should change your understanding of the space-time that we live in. Now we meet another giant, and this is Isaac Newton, and he was born in 1643 and lived to be 84. And of course you know that he had a big part to play in developing mechanics. So let's think about Newton's laws. And Newton's laws assumed that space was Euclidean and that time was absolute. And absolute time means that there's some kind of big clock in the center of the universe that just ticks, tick, tock, tick, tock, tick, tock. And this defines time universally. So Newton had three laws. Let's call them Newton 1, Newton 2, and Newton 3. So Newton's first law told us that in the absence of any interactions, then a particle or a body continues in its state of rest or uniform motion. Okay, Newton's second law told us that the force on a body, let's call it big F, and it's a vector, is proportional to the acceleration. And the constant of proportionality is called the inertial mass. And for reasons unbeknown to me, but I want to keep with convention, in this course we call acceleration little f. Okay, and if I changed it from anything else, then we would have to change a near infinite amount of f's to a's. So let me stick with the little f. So this constant is called our inertial mass. Okay, and you may know that Newton's law says that the force on a body is the rate of change of momentum. In this case, we're thinking about constant masses. So we have an inertial mass. So this is our acceleration. And Newton's third law tells us that every action has an equal and opposite reaction. So if I push on this panel, the force that I exert, I feel the same force back on my fingers. So the forces of action and reaction are equal and opposite meaning in the opposite direction. Okay, these laws assume Euclidean space and absolute time, but they also only hold in what's called an inertial reference system. So an inertial reference frame is one in which a free particle feels no acceleration. So that means there are no forces acting on it. And if we look at Newton's first law again, then we can read this as actually just being a choice of reference frame to one of these inertial frames. And an example of an inertial reference frame could be skydivers that have jumped out of a plane and they're falling towards the ground. Initially they are accelerating due to gravity, but air resistance kicks in and eventually they reach a terminal velocity where they fall at a constant velocity. So there are no net forces acting on them and they continue to move in uniform motion. Okay, so if you and your friends jump out of the plane, you will fall and maintain distances between each other and you'll fall at uniform velocity. Okay, so you can map out a coordinate system between you and your friends, and this is an inertial reference coordinate system. So relativity is all about transformations between different reference frames. And before we get to the special relativity, let's think about a Galilean transformation. And this is a type of transformation that we have intuition for because in our world of low velocities, so we go about the world at quite a low pace, this is what we have some intuition for. So this is a Galilean transformation. So let's think about two frames of reference. Let's call the first one S. And let's call the second one S bar. And S bar, we assume moves away from S with some constant velocity, u. So let's say at t equals 0, the two origins coincide. So let's think about a non-zero time, and at some time t, S bar moves a distance ut away from the origin of S. So we can write the position of our particle P in terms of a vector from the origin of S bar, and we call this R bar. And this R bar equals, and let's think about it, the point P from the position of the origin of S. So R bar, this vector, equals minus ut plus R. So we have an R minus ut. So let's think about what that means in terms of the velocity and acceleration. So our velocity v bar is equal to dr bar by dt. And this equals d by dt of the right hand side. So this is dr by dt minus u. And then if we think about the acceleration in the S bar frame, this is F bar, it's a vector. It's dv bar by dt. And it equals d2r by dt squared. And this is a constant velocity. So if we differentiate with respect to time, this is 0. So this is just F bar. Sorry, this is just F, the acceleration in the unbarred system. Okay, so we find that F bar equals F, and that V bar equals V minus U, and that R bar equals R minus ut. So these are the transformations for a Galilean transformation. So note that if the acceleration is 0 in one frame, so if our particle is a free particle, there's 0 acceleration, then the other frame also has 0 acceleration. Okay, so if the particle has 0 acceleration in one frame, it also has 0 acceleration in the other. So if one frame is an inertial reference frame, if the other moves with constant velocity u, the other frame is also an inertial reference frame. And we can't identify any kind of superior reference frame, so all inertial reference frames are as special or as unspecial as each other. And this transformation of velocity is what you know from experience. If you're sitting on a train, okay, here's a train or a bus. Let's say a bus, and this is the road, and there's someone standing on the road. And this person is standing still, and their reference frame is S, and the reference frame of the bus is S bar. And the bus is moving with velocity u away from the person standing on the road. Okay, thankfully, so they won't get run over. So if I'm sitting on this bus, okay, this is me, and I throw a ball with velocity v bar in my reference frame. So I'm sitting on the bus, I throw a ball with velocity v. From the perspective of someone in S, that velocity v equals v bar, so the velocity I throw the ball with, plus the velocity of the bus. Okay, so it looks to this person like that particle, that ball, is moving at v bar plus u. Okay, and it's not just that it looks like, that ball is moving at that velocity. Okay, so this is a Galilean transformation, and it's what we're all intuitively aware of. So we find that if S is an inertial reference frame, then so is S bar. Okay, and this is key. And Newton's laws are the same in all inertial reference frames. Okay, so this is just what we looked at when we thought about Galileo's ship. So everything was rosy with Newton's laws for a good 100 years or more. But then in 1831, this towering figure, James Clerk Maxwell, was born. He's a Scottish mathematical physicist. And at the age of 33 or so, he wrote down a unifying description of electricity, magnetism, and light. And he concluded that light travelled as a wave, an electromagnetic wave. And this begged the question, waves in what? So you know that sound waves travel through air, and water waves are propagating obviously through the water. So if light is travelling as a wave, what is it travelling through? So all the greatest minds in science were thinking about possible media, a medium that light can travel through. And this was termed the ether. And then the big urgent question at the time was to try and measure the motion of the earth through the ether. So there's a very good video, and I encourage you to press pause on this one and now go and watch the short couple of minute clip on the attempts to measure the motion of the earth through the ether, and maybe give a spoiler alert that these attempts failed. So if you watched the video, you will have seen that the Michelson Morley experiment failed to detect any kind of medium, any ether through which light travels. And there have been more recent experiments to try and detect this. So here's one from 2003 with optical resonators. And they all come to the same conclusion. There is no ether. So Newton said that velocities add. So we saw our Galilean transformation was v bar equals v minus u. But Maxwell said that the speed of light is constant. So Maxwell said that the speed of light is constant for all inertial observers. Okay, and if I ask you what the speed of light is, then maybe some of you will say it's c, let's call it c, and it's 2.99 something something times 10 to the 8 meters per second. Okay, and the question is meters per second relative to what? Okay, so in what frame? Well, the answer is in every frame, according to Maxwell. But Einstein came along and realized that these two worldviews were at odds with each other, and something was wrong. And he became obsessed with this problem, and he was inspired and had a great amount of admiration for Maxwell. And he made it his goal to try and solve this problem. And we know that he succeeded. So here's some photos of Einstein, young and old. And he became, as you know, a worldwide celebrity almost. And you even see a physicist advertising some Carlsberg beer. So instinct says beer, reason says Carlsberg. So thinking about this problem, Einstein said, well, okay, the Michelson-Morley experiment says that there is no ether. Whilst the other scientists tried to think about reasons why the experiment was a bad one, they just hadn't detected the ether because the experiment was flawed in some way. Einstein took a different tack, and he thought, well, let's assume there is no ether. How can I solve this problem otherwise? So he thought about two assumptions or postulates. And the first was from Maxwell, that the speed of light in vacuum is the same in all inertial frames. So this is just what Maxwell said effectively. But then he said further that the laws of physics, not just mechanics, are the same in all inertial frames of reference. And taken together, these two postulates lead to a new type of coordinate transformation that's different from the Galilean one. And we're going to derive that and see what the consequences are. So taken together, this gives us Einstein's special principle of relativity. So next we'll look at the consequences of these two postulates. And starting from a blank page, we're going to derive the coordinate transformation that results, and we'll see the profound consequences of it.